So it's really gives me a great pleasure and in fact an honor to introduce the plenary speaker, Professor David Nelson, who is an Arthur K. Solomon Professor of Biophysics, Physics, and Applied Physics, practically everything, at Howard University in Boston. He was also former chair of physics at Harvard. And among the numerous accolades that actually is too long list to cite, but I would like to mention the most notable ones. He was a MacArthur Fellowship, or he's a recipient of the MacArthur Fellowship in 1984. He was an American Physics Society Fellow in 1987. He also a recipient of Guggenheim Fellowship in 1993, elected member of National Academy of Sciences in 1994. He obtained a Bardeen Prize, and if you are not from physics, you may not know who was a Bardeen was. John Bardeen, who received 2 Nobel Prizes, by the way. He was the only one who obtained 2 Nobel Prizes in physics for semiconductors and superconductors. 2 in 2003, and he also obtained a Buckley Prize of the American Physical Society, 2004. So without further ado, I'd like to invite, and the stage is yours.
Well, it's a pleasure to be here in Kentucky, and an honor to address an audience of distinguished mathematicians who not only know all the subtle aspects of topology, which I barely can comprehend, but clearly, based on the banquet last night with the bluegrass music, also know how to have a good time. So it's great to be here. And I'd like to tell you a little story today inspired by the physics of a remarkable material, remarkable set of materials. We'll be talking about the physics of sheet polymers and some topological aspects, it turns out. What you see here is way back in the 1970s, people took electron micrographs of the so-called RAG phase of molybdenum disulfide, which I don't know about what you think, but to my eye, it looks an awful lot like a crumpled piece of paper. And the physics of crumpling and the physics of thin plates have been a challenge in mathematics and physics for, I like to convince you, for over a century. If you can compute the fractal dimension of this object, including the self-avoidance from the individual pieces of paper, it's about 2.3. If you actually measure it, you should publish. No one has been able to come close to answering that question analytically. What drew me back into this field a couple years ago were some remarkable experiments, not on molybdenum disulfide, which is a common lubricant, but on graphene. Graphene, some of you may have heard, is an atomically thin collection of carbon atoms arranged in a honeycomb lattice. And what these experimenters in Paul McEwen's group succeeded in doing was freely suspending, that is, without any support, just basically embedded in a water bath attached to the top, but a magnetic pad at the bottom. And they were able to actually get this atomically thin ribbon separated from the substrate and free to float around and be subject to Brownian motion and thermal fluctuations at room temperature. This had never been done before. This object is a kind of ribbon. You could think of it as a ribbon polymer, but it's an extremely unusual one. It's 50,000 times wider than it is thin. It's atomically thin. Reached the Moore's law limit of thinness with this object. And by just using this ordinary refrigerator-type magnet, you're able to twist it around, bend it, and just study its contortions in 3 dimensions. That's not all. They also made, by some laser ablation, a graphene spring. This is atomically thin. You can have 10,000 pulls on this graphene spring, and it still comes back. Seems to be remarkably robust to wear and tear. And if you think about what's going on with this graphene spring, many interesting things are going on, including the properties of the quantum mechanical electrons that carry currents in the plane of this object. It's an object that some people call kirigami because you're folding and bending, but you're also cutting. And you can sort of see that what's going on here, among other things, is if I take this hole, this frame, which of course changes the topology of a flat sheet, and pull on it, you can see what it wants to do is to escape into the third dimension. And this escape process plays an essential role in the elastic properties of that spring, as I hope to convince you do thermal fluctuations. And so with that introduction, I want to tell you a little bit about perforations and the crumpling of these freestanding graphene objects that are subject to Brownian motion. It's a kind of combination of very simple topology, but with some rather subtle physics and science coming from fluctuating metric tensor. And we'll see how that plays out here. I'll review the statistical mechanics of thin plates and the nonlinear bending and stretching energies. There's a dimensionless number, that tells you how hard it is to solve problems like this crumpled piece of paper or this frame buckling into the third dimension. A little bit like the Reynolds number in fluid mechanics. How many of you have encountered the Reynolds number in your studies? This is called the Foppel-von Karman number. It's a measure of how nonlinear the underlying equations are. This is even at zero temperature without statistical mechanics, and we'll talk about where this Foppel-von Karman number comes from and why it's so large. And then we'll talk about the effect of perforations, and we'll see that they trigger a kind of crumpling transition, a spontaneous crumpling transition, whereby at low temperatures, even in the presence of thermal fluctuations, this object might be approximately flat with some wrinkles superimposed, but at high temperatures, with the right perforations, it seems like it may go into a crumpled phase, and there's an interesting change of state, phase transition in between. And you can even get a crumpling transition with a single frame with a large hole, the kind that I've been waving around recently. And then at the end, if there's time, I'll tell you a little bit about curvature. And oftentimes, at least physicists are rather cavalier with boundary conditions, and we don't think it matters too much whether you have periodic boundary conditions or open boundary conditions in the thermodynamic limit for most properties. And we'll see that this set of problems is simply not true. And the statistical mechanics of cylindrical and spherical shells is significantly different. So here are some of my collaborators. And I'd also like to welcome questions as we go along. Please do interrupt and just let me know if something's not clear, and I'd be happy to pause and discuss it further. Any questions at this point? Have I made myself understandable? Okay, so here's a reprise of some 100-year-old equations, maybe 110 years old or something like that. You have a thin sheet of paper, thin plate, which wants to be flat, maybe at zero temperatures, but it can be subjected to various distortions. And there can be in-plane stretching, described by these displacements from some reference sheet, in-plane displacements U1 and U2. Physicists like to call those phonons. And then there's out-of-plane fluctuations as well, which we'll denote by F. There's this F field. And not surprisingly, certainly not to this audience, there will not be a lot of surprise, a little line element down here gets distorted by these changes, by the in-plane stretching and the out-of-plane bending. And that distortion is embodied, you can think of it as a change in the metric tensor, which is summarized by this stress tensor, Uij, which is shown here. If I know Uij, and I know the bending out of the plane, there's an energy that at zero temperatures would typically be minimized, subject to some boundary conditions. It's the same energy that would be minimized if you were to crumple this paper and require it to be in some sort of confined volume. And that energy has a couple parts. there's a bending energy here that actually goes like the Laplacian of this out-of-plane displacement field squared. And then there's these usual elastic constants, mu and lambda. They're sometimes called Lemay coefficients. They come from 19th century elasticity theory, which was only generalized to thin plates early in the 20th century. And then this strain tensor, which also contributes to the energy, has this remarkable form that's shown here. It's a symmetrized derivatives of these in-plane displacements, but the F field gets into the game because if I move out of the plane, I typically will stretch. And that stretching shows up here in this kind of nonlinear dependence on F. It's a little bit like a vector potential, a matrix vector potential that comes in, and it can lead to geometrical frustration and all sorts of interesting competitions between stretching energy and bending energy. So this is sort of sets the stage, and most of what I'll talk about today arises because of this very soft restoring force. It's a consequence really of rotational invariance of a freestanding sheet embedded in a liquid, or could be embedded in a vacuum also, if you like. It doesn't have to be water. And it's soft because it's a Laplacian, f to the fourth power, leads to very high derivatives in the underlying equations, leads to lots of mathematical challenges in trying to understand what's going on. So these nonlinear Foppel-von Karman equations go back to 1904, and if you associate with that stress tensor, that strain tensor rather, Uij, the nonlinear thing here, a stress, the force balance at every little place in the distorted elastic surface is given by this equation, and it's convenient to solve this equation by just setting sigma ij equal to the symmetrized derivative of an Airy stress function. And then we have the bending modes as well. And if you just minimize that energy over F and over the Airy stress function, just do some functional derivatives with Euler-Lagrange equations, you get these things here. This is a baby version of general relativity. In fact, down here you can see that the source in the Laplacian, biharmonic Laplacian squared sense for the Airy stress function that determines the stresses and strains, it ends up being this combination of derivatives of F, which is nothing more than the Gaussian curvature. The Gaussian curvature of this embedded surface in 3 dimensions is a source term over here, and then this is a bilinear nonlinearity over here that balances the bending forces on the right-hand side, and the only combination of elastic constants that matters in this Foppel-von Karman formulation is the Young's modulus, which is made out of the shear modulus, which is mu, and the bulk modulus, mu plus lambda. And it's not exactly general relativity. It's simpler. It also has the complication that extrinsic curvature matters, as it should for these crumpled objects. But it has this nonlinear flavor. Like general relativity, the exact solutions are only available in very special cases with certain boundary conditions. And as I'll show on the next slide, there's a Foppel-von Karman number, which I'll denote Vk, like Reynolds number is Re, which is the Young's modulus times the size of the sheet of paper squared, or the size of the graphene, if you prefer, squared, divided by the bending rigidity. And the problem gets hard when this is much, much greater than 1, and that's equivalent to saying that the sheet that you're interested in is extremely thin. And as I said, for graphene, we've reached the kind of Moore's law limit of thinness. So how big is this Foppel-von Karman number? Here are the equations again. You can rescale as you would in a fluid mechanics problem. And what you find is that this Foppel-von Karman number, which I'm going to argue is extremely large, appears as a reciprocal in front of the highest derivative in the problem, which is actually in this case the derivative of the F field. And if we work out and see how big this dimensionless coupling constant is, this is all about zero temperature science at the moment, you can take a piece of paper or a piece of crumpled tinfoil, exquisitely textured objects with hierarchical patterns of wrinkling, which, as I said, we still don't understand, even though we throw them in our trash cans almost every day. If you work out what this Fopl-von Karman number is, you need the 3D Young's modulus of this material. You work it out, it goes like the size of the sheet divided by the thickness squared. This is something called the Poisson ratio. Don't worry about it's not important for what I'm going to tell you about. For a piece of paper, a humble piece of paper, this Fopl-von Karman number is about 10 to the 7th or 10 to the 8th. Good luck doing perturbation theory in powers of 10 to the 7th. Graphene, it's really thin. And these are measured and calculated numbers at 0 temperature for graphene. Its Fopl-von Karman number is not 10 to the 7th, it's 10 to the 12th. So if you want a nonlinear problem which might have cascade of wrinkles in it when you crumple, not unlike the cascade that Kolmogorov, the great Soviet mathematician, and colleagues postulated for turbulent water flow, this is an interesting and rather promising and challenging area. Any questions so far? Okay, so here's just an illustration about, even at 0 temperature, these nonlinear problems are hard. So this is a simple experiment. We just take a plastic sheet and you put a grid on it, and then you systematically pull on it, and you just measure the force distance curves. It's like Hooke's law. You might think it's a spring, but it's quite a complicated nonlinear spring. And as I pull on this thing, you see it's escaping into the 3rd dimension. And as I go up on this plateau, you can ask, what do these curves look like? It's a function of the hole size. When I change a flat sheet into something which has a frame like character or the topology of a torus. Of course, flat sheets, if you try to pull on them, they're amazingly stiff. They just don't pull at all. You put a hole in there, and via this escape into the 3rd dimension, interesting things happen.
Question.
Please.
Multiple holes.
What about multiple holes? That's coming later in the talk. So thank you for that leading question. It was not planted. And I will come and tell about that as well. That's also quite interesting. And that's, of course, relevant to the graphene spring, which had multiple holes, which I showed at the beginning. Other questions? Please. Yes, there's something like a yield point. Thank you. And that's coming on the next slide, in fact. So here's how we think of these things. These are very precise measurements of a variety of force extension curves in these kinds of experiments. And one way to think about them, which has the idea of a yield point in it, but it's reversible, it's not plastic flow, is if I pull on something and I keep it flat, what am I doing in the corners? What I'm doing in the corners is I'm creating a mismatch away from the 90-degree angle that these corners want to have. So I pull it diagonally, for example. This angle will be a little less than 90. This will be a little bit greater than 90 degrees. And some of you may be familiar with an elementary defect, which I will attempt to illustrate here with shadow puppet kind of stuff. So here's a corner. And if I make the corner slightly smaller than 90 degrees, eventually I can even turn it over and make a cone. Okay? And what happens in the stress-strain curves in this simple but still challenging version of the Fopl-von Karman equations is what happens is you don't get a full conical disclination is the fancy name for the defect here, but you get a little bit of disclination charge, positive in this corner, same amount, positive in this corner, negative in these two corners. And then eventually, because the energy, when it remains flat, goes like s squared, but the energy, when it buckles into the 3rd dimension, like that cone, goes like s, you'll get a transition.
Question 2.
Please.
If the hole is circular, you don't have holes.
That's right. So it's good. If you have a circular hole here, what you get is a distributed continuum of disclination charge, much like the polarization of a sphere in electrostatics. But of course, this is a Laplacian squared kind of elasticity. but you get a distribution to go around the hole. But the square hole, just like electrostatics, when you have sharp corners, accentuates and concentrates the strain. So it's what they did with that spring, so that's what we chose to focus on. Other questions? Okay, so these partial disclinations at the frame corner buckle into the third dimension. When the force exceeds a critical value that makes the disclination charge, it's just the angular deficit relative to 90 degrees associated with these corners, and that critical value you can estimate in terms of the elastic parameters, depends on the Foppel-von Karman number, which is quite large. And it determines basically the analog of a yield stress. And here I just have a very steep linear curve, f proportional to x, corresponding to the intrinsic Young's modulus of a piece of paper without a hole. But then these disclinations buckle, and you get a shoulder and a plateau region until you stretch out the extra available area in the hole, and the force starts to go up again. So that's one simple way of understanding a particular problem. This is at zero temperature, however. So what about statistical mechanics? Well, if you go back to that energy, let me go way back here to this energy that I was showing you earlier. So I think it's this one right here. And I basically want to exponentiate this energy, put a minus sign over kBt, and ask, okay, now I'm in a thermal equilibrium with a thermal bath. What is the statistical properties of the force extension curve? What is the characteristic size? And this energy that gets exponentiated into a Boltzmann factor when we do statistical mechanics only depends on the in-plane elastic the displacement fields quadratically. There's non-trivial powers of f when I square out this strain tensor, but I can just integrate out those in-plane phonons, and that simplifies matters a little bit. And so when I do that, and I get back to where I was, trace out these phonons, e to the minus energy divided by kBt, and you get an effective free energy, which is a massless field theory that has in it this bending energy that I talked about before. But now those in-plane phonons generate an effective interaction between gradients of f that's quartic in the gradients of f. This is a transverse projection operator, and this is the Young's modulus, which acts as an elastic constant for this problem. So if I want to understand the fluctuating ribbon in Paul McEwen's experiment, for example, this is the kind of problem I would need to solve. And standard way that physicists and others like to look at these kinds of nonlinear field theories is perturbation theory, and now we have to do functional integrals over all possible complexions of the F field. So if it were a low temperature phase and I would be reasonably flat, I'd want to integrate over all possible smooth functions weighted by this strange looking energy here. And a systematic way of doing that is with Feynman diagrams. So you just do standard kind of thing that Richard Feynman taught us how to do in quantum electrodynamics. And I'm going to just show you one particular calculation, which is, I think, rather revealing of this bending rigidity. So this is a renormalized bending rigidity. It tells you how strong the system is with a background of thermal fluctuations. And you can see that those have the potential of having a rather striking effect, because this is actually an identical piece of paper. I just haven't wrinkled it. Look how pathetically weak it is. It can't hold its own, can't even hold itself up against gravity. This one has no problem. Okay? So these are not actual thermal fluctuations, I hesitate to add, but they think of them as a proxy, those wrinkles for thermal fluctuations. So if you calculate what the renormalized bending rigidity is with a background of thermal Brownian motion, you'll find something that's proportional to temperature. It's a low temperature perturbation theory, basically assuming that these gradients of the F field, which are proportional to the normals of the surface, assuming they're small, you get in Fourier space this kind of thing, and then if you go to the limit of small wavelengths, so you're looking at a long, small Q, a long wavelength bend, you find that the bending rigidity is corrected, and it looks okay at first sight because you have temperature as a coupling constant. That's pretty small. And then you divide by kappa. That's about 50 times room temperature, it turns out. 32 pi cubed, that's really going to help make this small, but it's multiplied by the Foppel-von Karman number. And that comes in, that the overall size of the system comes in because this integral is actually badly divergent for small wave vectors. You can just work it out, and it just blows up with system size in a very dramatic way. One thing you can do, which I did many years ago with Luca Politi, is to say, okay, this is just the result, this correction here from this first Feynman graph here. This is not going to be mathematically rigorous, I have to hasten to say, but it's a kind of standard trick that seems to work well in a number of problems involving critical phenomena and massless phases. Take the most singular contribution here, which is displayed here, the most singular contribution of second order in perturbation theory, third order, fourth order, sum it up, and what you'll get is an integral equation for the bending rigidity, where the renormalized bending rigidity appears here, and then it appears down here also, the fully dressed renormalized thing. This is just a Dyson equation for this renormalized bending rigidity. That's an integral equation which you can solve, and remarkably, you find that the bending rigidity becomes strongly wave vector dependent. It goes like 1 over the wave vector. So as I go to longer and longer wavelengths, making Q smaller and smaller, this bending rigidity gets bigger and bigger and bigger. The elastic constants, when thermal fluctuations are taken into account, are not in fact constant. They are scale dependent. There are other problems in physics, like the electrical conductivity of a dirty metal in 2 dimensions, where there's a logarithmic breakdown of Ohm's law. Here, there's a violent breakdown of Hooke's law, which is far stronger than a logarithm. So you can take this problem and then look at it using somewhat more sophisticated techniques. This was done back in the 1980s. And then when graphene became fashionable in physics, the best calculations were probably done by Pierre Ledussal and Leo Rodzachowski. And they finally wrote up how to calculate in the Annals of Physics, which just appeared. The bottom line, all you need to know for this talk, is that there's a renormalization group flow as you look at this problem systematically on longer and longer wavelengths, focusing on larger and larger length scales, from a Foppel-von Karman fixed point. That's the Foppel-von Karman equations that I was just talking about. These are already quite hard. And there's a flow that you get from these renormalization group techniques with running coupling constants to a new thermal Foppel-von Karman fixed point with scale-dependent elasticity. And that's indicated here. So if I have a 10 micron by 10 micron square of graphene of size L, so L might be 10 microns, then the actual bending rigidity depends on the size, the edge length, divided by some thermal parameter, which I'll talk about in a minute, raised to a non-trivial critical exponent power, eta. And that theory, that self-consistent theory I showed you earlier, eta is 1, but these more sophisticated theories show that eta is about actually 0.82. And similarly, the Young's modulus, which is the resistance to in-plane stretching, softens in a scale-dependent fashion. It softens like 1 over L to the eta u, and here's another critical exponent that's about 0.36, and you can see that there's softening with a piece of paper. There's lots of stored area in this thing because it's wrinkled, and if I pull on it, that area comes out and the system softens. So that's where the theory stood in the 1980s. Then came graphene. The first time we could take an individual sheet polymer, which should be describable by these kinds of ideas of a bending rigidity and in-plane nonlinear strains and so forth. Density functional expert calculators at 0 temperature have calculated the bending rigidity. They know that extremely well. It's 1.2 electron volts at 0 temperature. They know the in-plane Young's modulus, that's been measured, also calculated using sophisticated quantum mechanical calculations at 0 temperature, 20 electron volts per angstrom squared. I've already mentioned we've reached the Moore's law limit of thinness, and the Foppel-von Karman number is, dare I say, astronomical. Astronomical in the context of what I'll show you is a tabletop experiment. And if you take, and I didn't realize this until Paul McEwen pointed it out to me, if you go back to this little calculation, you can ask what size square of graphene would I need so that this perturbative correction, which multiplied by the Foppel-von Karman number, becomes comparable to 1. What size would I need? All sizes bigger than that, I'm going to have to worry about thermal fluctuations. Okay? So I just equate this thing to 1, and modulo various pi's and so forth. You'll get this thermal length. That also comes in here, normalizing the bending rigidity, running bending rigidity, the running Young's modulus. In fact, if you work that out for graphene, at room temperature, that length above which everything is going to drastically change due to these thermal effects is about 2 angstroms. So you better pay attention. That's, I think, one of the interesting aspects of this problem. And so what they did at Cornell was to measure with a cantilever experiment and various other ways the deflection of a ribbon of width W, about 10 microns. They did various lengths. They're an excellent company. This was done by Galileo in 1638. But in this modern version of the cantilever, for graphene, this slope here gives the bending rigidity. If the bending rigidity in this log-log plot were what the quantum mechanical experts at 0 temperature claim, it would be 1.2 electron volts. Instead, it's 7 kilo-electron volts for a 10 microns wide ribbon. So it's been amplified by 4,000. 4,000 isn't big enough for you. You can do it for 100 micron with wide ribbon, and it will be 40,000 times bigger or something like that. So these running coupling constants appear to be real and have important consequences in room temperature applications of graphene. So these flexural phonons, these out-of-plane phonons, which, by the way, you could sort of understand why this is so strong. This is so pathetic, this piece of paper here. This has all these background wrinkles, and so if I actually try to bend this on top of the background wrinkles, I'm going to get Gaussian curvature somewhere, lots of places. And the elastic shear modulus fights Gaussian curvature, and that's one way of thinking about why this thing is so strong. These flexural phonons that interact with the Gaussian curvature, they boost the bending rigidity, but it's worth remembering that living in these graphene sheets are electrons, which are highly quantum mechanical, even at room temperature. And these are electron creation and destruction operators for fermions. And when they have the flexural phonons acting, that stretches the bond lengths and couples to what the electrons are doing via this hopping matrix element, which typically depends exponentially on the average distance Aij. So there's an electron-phonon coupling in this problem. This is the usual one that people who work on superconductivity know and love. This is a phonon here, an in-plane phonon. These are the flexural phonons that I've been talking about, and they couple to the electron creation and destruction operators. I don't claim they cause superconductivity, but they do other things. I know, a Moiré bilayer, and it would be interesting to look for some of these effects. Most of those, the questioner is alluding to some recent discoveries of Moiré patterns where you put one graphene sheet down and you rotate by some magic angle, put it down on top, you get a Moiré pattern, and that object is superconducting below 2 degrees or something like that. Those objects, and most of the literature on graphene experimentation, unfortunately from my point of view, are done with the object plastered onto a substrate, so no flexural phonons. But they're quite interesting in their own right. I'd love to have them liberated and see what fluctuations in a background curvature, fluctuating curved space due to superconductivity. That would be fun. So we've seen that the flexural phonons boost the bending rigidity, and we have an arena to study the in-plane electrons. They're basically look mathematically like Dirac fermions with a fluctuating background curved space that mimics general relativity. It doesn't get any better than that. Physicists are supposed to love that stuff, and we do. If you work this out in the flat phase, you find there's something called the electron dephasing rate, which depends on how the chemical potential of the electrons relative to the Dirac point. And this exponent eta, this thing that's 0.82, appears in this quantum mechanical quantity. So we have what we call soft condensed matter, the physics of polymers, meeting hard condensed matter, the physics of Dirac electrons, in this intriguing way. And in the rest of this lecture, one of the things I want to explore is, can the extreme statistical mechanics of this kind of wrinkled object, with its coupling to the quantum mechanics of the graphene electrons, be amplified even further? Could I make the object crumpled into something truly interesting? And you might guess that if you just turned up the temperature, you could do that. And the kind of order parameter that describes the broken symmetry of the flat phase is the normals. So I imagine even if it's mildly wrinkled, I look locally at the normal to this sheet of paper, and if the paper is macroscopically flat in the thermodynamic limit of large paper size, the normal here should be correlated with the normal on the other corner. And as I pull the normals apart, I have long-range order, much like a spin system of Heisenberg classical unit vectors, field of normals perpendicular to the surface. And you can work out the normal-normal correlation function. Here's the math that is just sketched for you here. And normally, if this bending rigidity, this elastic constant were actually a constant and independent of wave vector, this would be logarithmically divergent. And there's a famous theorem that says in many two-dimensional systems that might have a broken symmetry, thermal fluctuations will overwhelm that broken symmetry. In fact, that's the kind of thing that Mike Kosterlitz might have talked about earlier in this week. In any event, as I take the normals up further and further apart, I can work out this normal-normal correlation function. It goes to a constant at low temperatures. Here's how it goes to that constant with this power law. And then there's this suppression relative to 1. If we're perfectly flat, this correlation function would be 1 at large distances. It's suppressed, and at low temperatures, when kBt over 2 pi kappa is small, this presumably is a description of the correlations in the flat phase. And that's what I've been talking about for most of this lecture. And in this flat phase, I have wrinkles, to be sure, but there's still a projected area that goes like the overall size of the graphene sheet squared. But suppose the temperature is high enough, eta is of order 1, this logarithm is of order 1, so high enough so that kBt is of order 2 pi kappa, then this could go negative in principle, according to this calculation. That can't happen. There's something strange going on, and that, you might argue, is a crumpling transition, an indicator of where the crumpling transition would occur. And so here's a cartoon of that object, and its projected area related to the fractal dimension of this object, which I hope some of you mathematicians will explain and understand. I would love to know its fractal dimension from some first principles analysis. Its projected area doesn't go like L squared, it goes like L to the 8/5, corresponding to a fractal dimension that's neither 2 nor 3-dimensional, maybe more like 2.5, 2.4. So, okay, great. So we go out, we find our experimental friends, and perhaps over a beer, soften them up. Say, oh, raise the temperature, look for the crumpling transition of graphene. And they'll say, okay, what temperature should I use? And then you estimate what that is from this criterion. And sadly, it's 20,000 degrees Kelvin. Okay. Not going to happen. The water's going to boil well before you get there. You do it in a vacuum, the chemical bonds will fall apart before you get up to this temperature. And then they'll laugh at you and so forth. Well, they didn't actually do that. We realized they would laugh at us. So we went back, and as per the question we had earlier, we considered what would happen if we punched a lattice of holes in the graphene. Soften it up a little bit, make it a little more flexible. And so this is perforated graphene. It has a very interesting topology, of course. I want to argue that this does have a crumpling transition in an experimentally accessible range. This is something called the radius of gyration as a function of the bending rigidity, a rescaled bending rigidity divided by kBt. And there's a dramatic jump in the radius of gyration. At low temperatures, it's flat, so the radius of gyration, let's say, follow this blue curve, is large, and then it undergoes a very abrupt transition as it crumples. And as a function of the removed area, we can calculate the crumpling temperature. It's shown here, and we get this interesting curve, this green curve, and we roughly know it should be dropping once we add the holes, but we don't know the details of this drop. But we can estimate from these computer simulations, which I'll show you in more detail in a minute, that if you can remove 85% of the area, you can get this crumpling transition down from 20,000 degrees Kelvin to 1,600 degrees Kelvin, which is probably accessible for graphene in a vacuum. Yes, please. It will depend. In these experiments with a periodic lattice of holes, it seems to just depend on the fraction of removed area. These are different flavors of holes. There seems to be a universal master curve. But there's an extreme version of your question, which I'll come to, which is what happens if I condense all the holes into one giant hole to make a frame? Well, I will come to that. Thank you for that question. Other questions?
It's related, so I thought
Yeah.
it was slitting.
Slitting is a wonderful idea, and if you... Yeah, absolutely. So that's one of my dreams, is to understand how to handle slits. And that's a harder problem. But it's clearly going to soften up the surface in an interesting way. And if you've ever played with a slit, if you pull on it transverse to the direction of the slit, it does soften, and the thing forms lips and buckles into the third dimension. But if you pull along the slit, it's still stiff. And so our idea was to, as probably the same as yours, is to lay down a regular lattice of slits. So here's a piece of paper, and we have a family that looks like this, another family that looks like this, and maybe put them at three sets of angles at 120 degrees. My guess is that will crumple, but we have not studied it, but it's a fascinating question. Yeah, you can certainly do this experimentally as well. But I think the best candidate for what I'm going to talk about ultimately is to have, at least to start with, is to have one giant hole. But I think of it like if you're cutting the tendons of the graphene with these slits, and you cut enough of them, it's going to flop like crazy. And even while it stays intact, overall, you don't cut it in two, it should start flopping like crazy. And it's kind of a percolation question, a percolation of rigidity. So that's a great question. Thank you. Other questions? So I remind you that we want 85% of the material removed. They've already removed 40% with this graphene spring. But I still haven't persuaded Paul McEwen to do the experiment. But we have done these cool simulations. So here's a simulation where the blue is no holes, the red is whatever it is, 70% or 60% of the material removed. And you can see it's a lot floppier. This is below the crumpling transition. TC stands for T crumpling. Whoops, sorry. So here it is when you're in the flat phase locally. Here it is when it's crumpled. Here it is when it's right sitting at the phase transition. It doesn't know whether to be flat or crumpled. And if one could get into this regime, we know next to nothing about the mechanical properties of this object at the critical point. Thank you, 5 minutes. There are lots of cool questions. And then, as has been alluded to by members of the audience, what happens if I take these holes and I condense them into one giant hole in the middle, either a square hole or a hexagonal hole? I won't go through the details except to say that we've done some simulations and looked at the correlations of the normals, say the normal at A compared to the normal at D. And there is a kind of transition where these are correlated on opposite corners. You go to high enough temperatures, then they start flopping around and the normals no longer know what's going on. So if I go to high enough temperature, the normal correlation function goes to 0. That's accompanied by a singularity in the specific heat. So summarize, someone asked what about the size of the hole? Well, you can vary the size of a square hole, for example, and you go from this flat thing where the tiny hole isn't going to make a big difference. You put a pinhole in a piece of paper, it doesn't change it. Make it big enough, it seems to crumple, and we actually think, although it sort of looks like a ring polymer in the end, it does. If you take the thermodynamic limit and study the size, which is the fancy name is this radius gyration, and put in the appropriate scale-dependent bending rigidity depending on the width of the frame, we think that an appropriate limit of L going to infinity, that's the size of the frame, the width of the frame going to infinity, with this ratio fixed, this eta-dependent ratio fixed, we think there may be a sharp phase transition. So I want to end by one more thing that might interest perhaps the topologists in the audience, and when you combine it with curvature. And I want to argue that curvature matters for the statistical mechanics. I've been talking mostly about this object. What would happen if I took the graphene and wrapped it around to form a cylinder? Or I made a sphere, a giant buckyball. And I want to argue that although a lot of times in physics we think the detailed boundary conditions don't matter for the local microscopic physics, here it does matter, and it matters with a vengeance. And I'll just briefly sketch the math. There's something called shallow shell theory, which you can do with two locally different radii of curvature, or Gaussian principal curvatures here, 1 over R1, 1 over R2. And you go through the same math that I've been using to describe what's going on in these ribbons. And you find it's the same stress tensor, the same stuff, except there's a new term, which depends on F linearly. It breaks the symmetry. Positive F is different than negative F, as you might expect if there's a background Gaussian curvature or even a background cylindrical curvature. And it goes like, the extra term goes like 1 over the radius of curvature, the principal curvature at that point. And if you work through the math, as I close up here, you discover that massless field theory requires a new term. And if we take the spherical limit, where the r's are equal, what happens? Well, this 1/2 kappa q to the 4th acquires a mass. The Gaussian curvature generates a kind of mass that's proportional to the Young's modulus and inversely proportional to the radius squared. And that changes the physics. And you can think of a sphere, if you look at the outward displacements of a sphere, that's what F is representing here. It's going to feel the stretching, restoring force associated with the Young's modulus because it's a sphere. Whereas a sheet of paper, if I just change F, it's translationally invariant, nothing's going to happen. Even for a cylinder, interesting things happen. A cylinder, you get this weird looking term here, and you can think of that as an angle-dependent mass. And I'll wrap up by just saying what happens in these 3 cases. To a very simple quantity, the root mean square vertical fluctuation of the sheet. How does it depend on the size? Okay? It's sort of like a Lindemann criterion, but it's the vertical fluxural phonon field that I'm talking about. So an L by L sheet, if you work that out and you use this renormalized bending rigidity that I've been talking about with the exponent eta equals 0.82, after some math, you find that the mean square fluctuations of this height, they scale with the system size. They get bigger and bigger, but it doesn't go like L squared. It goes sublinearly with L, so that means you're sort of in a flat phase, but with a lot of fluctuations, and it goes like L to the 1.18. That's for a flat sheet. What about a cylinder? Well, with a cylinder, you have that weird extra term out here. This is angle-dependent mass. You integrate over angle, you integrate over q's and stuff like that. And this integral over angle, it's like adding an extra dimension to the problem. Here's the two-dimensional integral over Fourier space. There's an integral over theta, which up here is sort of trivial. It just gives 2 pi. Now it has something in the denominator, and so it adds a dimension, and the result is different. You get L to the 2 minus 5 eta over 4, L to the 0.98. And then finally, for a sphere of radius r, now I get a mass, and you go through the math, and it's now goes like the size, which in this case is r, to the 0.77. Yeah, we should do it for a Moebius strip, which is a symbol of this conference. We haven't, but we should for both. Any event, you see that this local quantity, this up and down fluctuating quantity, which I would have thought wouldn't matter, wouldn't be very different from here, here, or here, because in the energy, the size of the system appears as a coupling constant. It's a new kind of renormalization problem. Because of that, there are these universal numbers, 1.18, 0.98, 0.77, that characterize these shapes at large distance, which is, I think, an interesting result for the interaction of metrics with topology. And those are the results I've been talking about. And I'll just briefly say that I won't have time to tell you about this, but if you take a sphere and you make it big enough at 0 osmotic pressure difference, the same kind of physics will crush such spheres whenever they're larger than 1,600 angstroms. So if anybody tries to sell you a graphene parachute, think twice, because it's going to thermally crumple. Thank you for your attention. Because our skin will be so much tougher and resilient. However, it will also become more brittle. And so don't stay out in the sun too long. Yes?
So one thing that I played with last summer at Short Grossberg and a few other people, was something you can see in these is the length of valleys and ridges.
Uh-huh.
Such things. I'm just wondering whether either on an experimental or theoretical.
Yeah, that's a very... I've thought about it, but I don't have much to add. You probably know that people like Tom Whitten at the University of Chicago have interesting things to say. When I look at this, I think of the large Foppel-von Karman number, and I think of the Kolmogorov cascade of length scales in fluid mechanics at high Reynolds number and turbulence. And there's something like that going on here. And of course, eventually we'd want to put in self-avoidance, which would make the problem even harder. But it's a fascinating problem, and I hope you and Shura can solve it. Well, there's a Kolmogorov exponent, which is 5/3, which has nothing to do with my exponents. And also, I should say that the turbulence is a dynamical phenomenon. And there are dynamical questions. If I put this in water, how does it fluctuate? I put it in air, how does it fluctuate? I'm just talking about a nominally simpler problem, which is the static equal time correlations. But, yeah. Sure.
Can we predict the behavior of bilayers with Moebius pattern, and then what would happen if we disturb that Moebius pattern by creating bowing?
I can't, because I haven't tried to do it. But I think it would be fun to look at Mare patterns. But again, the crucial thing would be to lift the Mare or whatever problem you're interested in, whatever bilayer, graphene problem, or molybdenum disulfide, et cetera, off the substrate. Because what does the substrate do? it creates, on top of the kinds of energies that I've been talking about, it creates an F squared term, because it's the force squishing this sheet. So if this sheet is on a substrate, and that substrate is pulling it down, it irons out the wrinkles, and it's a fascinating problem in its own right. What is the electrical conductivity of a moire pattern like this, squashed onto a substrate? But it's not going to have dramatic flexural phonons, because you will have tamed them by having interaction with the substrate.
Another question. Has anybody studied the in situ, or measured, sorry, the in situ phonons while this is stretching,
Perhaps with some kind of scattering experiment, one could do that. And as far as I know, that's been done for graphene, but not freely suspended graphene. It was only graphene on the substrate on which it was grown.
Yeah, sure.
Yes, please.
So this is about the flat versus cylindrical versus.
Yeah.
So we're used to seeing, like, when you take a large limit of a sphere or a cylinder, it being like a flat.
Yes.
Is there a way, a different way of looking at this? Is it going to see that kind of.
How do we evade that expectation? Okay, so the question, if I could repeat it, is if you look locally at a cylinder or a sphere, it looks flat. You have to go out some distance to notice that there's some sort of background curvature. And I wish I had a better intuitive way of saying it, but I can say that those principal curvatures come and modify this energy, this effective free energy, or think of it as a Hamiltonian, in a profound way. Why is it profound? It's profound because, as I said, before I just had gradients of F, and the system was rotationally invariant. So if I take this wrinkled object and I just rotate it, that produces gradients of F, and the energy doesn't change. But when I have the topology of a cylinder or a sphere, you get something that is just linear in F. It has no gradients at all. There's an inside versus an outside of a cylinder and a sphere. And one way to think about it is, if this were a little patch of a sphere, and it were curved around to make a whole sphere, those thermal wrinkles, which are so easy to accommodate in an accordion-like fashion in a piece of paper with free edges, are actually crushing the sphere inward. And it's that topology of the sphere that transforms these normal fluctuations into a kind of inward effective pressure that allows, in my opinion, an understanding of why this simple expectation that you referred to breaks down.
So I was thinking back to some old simulations that Gary Grass did many years ago.
Sure.
He punctured the random surfaces with holes randomly.
Yes.
And certainly you could imagine doing that experimentally with radiation or something.
Sure.
And I'm wondering whether you could, of course, what he found is the flatness exponent.
Mm-hmm.
Scaling were invariant through that process all the way up to the point where they flew apart.
Yeah.
That was really instructive at the time. Because,
Yes, it was.
but then again, whether if you raise the temperatures, whether that mode of incorporating the surface
Mm-hmm.
might lead to crumbling. It's quite realizable.
Yeah, I'm hoping, if Gary's interested, we had extensive conversations back in those days, to have him revisit. And what I think would be really cool, so if you see him, have him give me a call. We're old friends, would be to do this, right? This is really easy. And so one of the things in those days that Gary quite rightly pointed out, when you put random perforations, all we've done is a lattice of them, it's not so different, is that, as Gary pointed out, distant self-avoidance fights crumpling. It doesn't stop me from doing this, but the simulations I've shown you, I should have emphasized this, were without distant self-avoidance. And so the argument was, well, with distant self-avoidance, it'll always be in the flat phase. And this is a way around, this is a way of exploring that, forcing the issue with a single large hole. This is also done without distant self-avoidance, but this has got to be a ring polymer, and self-avoidance is going to have a mild effect on it, but it's not going to change the fact that it crumples. So we think that, have Gary give me a call, or you can give me a call. I'm happy to talk to anyone about simulating this kind of thing with distant self-avoidance. Let's find out if there's a phase transition here first, and then let's go back to the fascinating question of holes and raise the temperature as you're suggesting. Yeah. Right. Yes. Yeah. There's a delicate interplay between issues like self-crushing of spheres, which will happen to any sphere when it gets big enough, and the flat phase, which survives in the thermodynamic limit. We need to put those things together. We need to ask mechanical questions. What happens when I pull on these floppy objects? And it's a kind of a new kind of percolation theory, as was pointed out. The slits would be another very cool thing to look at.